Good morning, students. Teacher Betty, continuing with the nuclear chemistry, lesson 4. In lesson 2, we looked at the factors which affect the stability of the nucleus. And the factors were binding energy of the nucleus. Here we said that when protons and neutrons combine, mass is lost. This mass is converted into energy, and this energy is known as the binding energy. Binding energy, therefore, is the energy required to decompose the nucleus into its constituent neutrons and protons. Another factor was the magic number, or the shell model. This model believes that each nucleon moves in its own orbit within the nucleus. And each particle within the nucleus is paired among itself. For example, the neutrons are paired among the neutrons, and the protons are paired among the protons. The nuclear shell containing the specific number is said to be stable. And this specific number is known as the magic number. And these magic numbers are 2, 8, 20, 28, 50, 82, and 120. They were also classified into 2. We have the single magic number. Here, one of the particles is having a magic number, either a proton or a neutron. Then another one is the double magic number, where both the particles are having the magic number. That is, a proton is having a magic number, and the neutron is also having the magic number. And it is believed that the nucleus, which has particles which have got magic numbers, are referred to as stable nucleus. Today, we are going to look at the nuclear reactions. You can ask yourself, what are nuclear reactions? These are reactions in which one element is converted into another element, either by emitting an alpha particle or a beta particle. That is, an element undergoes a spontaneous disintegration with the release of an alpha particle or a beta particle, or an element can be bombarded with a suitable particle, and that one is known as artificial transmutation of the element. In these reactions, the number of nucleons present in the nucleus of an original element changes. We can say that in a nuclear reaction, transformation or transmutation of atoms take place. Let us now look at the differences between the chemical reactions and the nuclear reactions. In a chemical reaction, only the outermost electrons of the participating atoms take part in the reaction, and the nuclei of the atoms remains unaffected. Whereas in a nuclear reaction, the nuclei of the atoms undergo a change in their composition. In a chemical reaction, the identity of an element remains the same even after the chemical reactions. That is, no new elements are formed. Whereas in a nuclear reaction, one element gets changed into another element or elements. That is, new elements are formed. In a chemical reaction, a small amount of energy is absorbed or released in these reactions. Whereas in a nuclear reaction, a large amount of energy is absorbed or released in the reaction. In a chemical reaction, these reactions are greatly affected by change in temperature, pressure, and other factors, while in a nuclear reaction, these reactions are not affected by change in temperature, pressure, and other factors. In a chemical reaction, these reactions can be reversible under suitable conditions, while in a nuclear reaction, these reactions cannot be reversed. And lastly, in a chemical reactions, all the isotopes of an element give the same type of chemical reactions, while in a nuclear reaction, all the isotopes of an element give different type of nuclear reaction. Classification of nuclear reactions. They can be classified. The first classification is based on whether the nuclear reactions take place spontaneously or is brought about by artificial means. This first classification is divided into two nuclear reactions. The first one, the nuclear reaction in which a radioactive element spontaneously disintegrates into another element by emitting alpha, beta, or gamma rays. In this case, a single radioactive element is involved. An example is of a radioactive element is uranium-238, which disintegrates into another radioactive element, the thorium-234, and an alpha particle is emitted. Then this unstable radioactive thorium also disintegrates into protactinium-234, and an emission of beta particle is observed. The second classification. This classification is based on the nature of the bombarding particle or the projectile used in the nuclear reaction. The particles which are generally used as bombarding projectiles are the alpha particles, the protons, neutrons, tritons, gamma rays, and others. The third classification is based on the overall energy transformation that occur during the nuclear change. We also have the following types of reactions. The first one is the capture reactions. These are the nuclear reactions in which bombarding particle is captured by the target nucleus with the emission of the gamma photon. An example is lithium-7, which captures an alpha particle to give boron-11, and also a gamma ray photon is emitted. The second one is the carbon-12, which captures the alpha particle to give rise to nitrogen-13, and the gamma ray photon is emitted. The second type of reaction is the particle-particle reactions. In these reactions, the bombarding particle is absorbed by the target nucleus to form the unstable compound nucleus, which half-life period is 10 to the power negative 14 to 10 to the power negative 12 seconds. These compound nucleus break down or disintegrates to form the stable nucleus. An example is sodium-24, which is bombarded with an alpha particle to give an unstable nucleus of aluminium-28. This one disintegrates into aluminium-26 and an emission of 2 neutrons. Another example is magnesium-26, which is bombarded with a deuteron to give rise to an unstable nucleus of aluminium-28, which later disintegrates to give magnesium-27 and a proton. The last one is the spallation reaction. This is a nuclear reaction in which a high energy incident particle or a photon causes several particles or fragments to be emitted by the target nucleus. The mass number and the atomic number of the target nucleus reduces by several units. An example of a high-speed particle is an alpha particle, which has got an energy of 400 electron volts. This one converts copper-63 nucleus into chlorine-37 nucleus, releasing 14 protons and 16 neutrons. An illustrative equation, copper-63 bombarded with an alpha particle to give rise to chlorine-37 and 14 protons and 16 neutrons are emitted. Another reaction is the fission reaction and also the fusion reactions, which we are going to see in the next lessons. The first classification is based on the fact whether energy is absorbed or released in the nuclear reaction. Also, this classification gives two types of nuclear reaction. We have the endogenic nuclear reaction. This is the same as an endothermic reaction. In these reactions, energy is absorbed by the reactant. And here, the sum of the masses of the reactants is less than the sum of the masses of the product. In other words, mass is gained. The mass increased is converted into energy, which is absorbed in the reaction. Energy absorbed in a given nuclear reaction is given by the Einstein's mass energy equation, which is E is equal to mc squared, where E is the energy absorbed, m is the mass gained, and c is the velocity of light. If the increase in mass is in mu, then the energy absorbed is equal to increase in mass times 931.5 electron volts. Remember, in the previous lessons, we said this will be seen in details in the coming lessons. Example of an endogenic reaction is in the Rutherford's artificial transmutation reaction. Here, the nitrogen-14 is bombarded with an alpha particle and a larger quantity of energy is absorbed to give rise to oxygen-17 plus a proton. So the masses of the reactants is equal to mass of nitrogen-14 nucleus plus mass of the helium nucleus, which is equal to 18.0057 mu. Mass of the product is equal to the mass of oxygen-17 nucleus plus mass of the proton, which is equal to 18 plus 0069 mu. So increase in mass is equal to the difference between the mass of the product and the mass of the reactant, which is equal to 0.0012 mu. Therefore, energy absorbed is equal to the mass increase times 931.5 millielectron volts, which is equal to 1.117 millielectron volts. Since the energy is absorbed in a given reaction, the given reaction is known as an energetic nuclear reaction. Another type of energy reaction is the exergic nuclear reaction. In these reactions, energy is released. The energy released in these reactions is called nuclear energy or the atomic energy. In these reactions, the sum of the masses of the product is less than the sum of the masses of the reactants. That is, mass is lost. The mass lost is converted into energy, which is released in the reaction. The energy released is given by the mass energy equation, which is E is equal to mc squared, where E is the energy released, m is the mass lost, and c is the velocity of light. But if the mass lost is in mu, then the energy released is equal to mass lost times 931.5 millielectron volts. An example of an exergic nuclear reaction is the fusion of the two deuterium nuclei to form a helium nucleus. So masses of the reactants is equal to 2 times masses of one deuterium nucleus, which is equal to 4.02942. Then mass of the product is equal to the mass of the helium nucleus, which is equal to 4.0026. Therefore, the mass lost is equal to the difference of the two masses, that is the mass of the reactants and the mass of the product, which is equal to 0.02682. Energy released is equal to, we multiply this mass lost by 931.5, which is equal to 24.9828 millielectron volt. An assignment I can leave you with: write a brief note on the Bohr's theory of the nuclear reaction. Next time, we are going to look at the nuclear fission.